Okay, so in our previous video we looked at histograms. We're going to continue to look at histograms here, but we're going to look at examples where it is useful to use a logarithmic scale or a log scale. So here we have a table of data and it shows the population of a number of Australian cities. Now if we were to create a histogram of the data, we want to think about, what would be difficult about working with this data in terms of creating a histogram. So bearing in mind this is discrete numerical data, so the main reason we would use a histogram for discrete numerical data is if we're going to group the data, and grouping of the data would certainly be necessary here because it ranges from just under 50,000, this 49,079, right up to over 2 million. Okay, so the span of the data is enormous, so we would certainly need to group it. But even when we do group it, deciding on the class interval widths is difficult, because really the data span is really quite great. So the biggest challenge here is the large span of data. So, big range, I guess. The range is large. Let's say large range, to use the technical word. So even if we were to group it in class intervals of width 100,000, our histogram would look like this. So obviously we've got, 4 cities with populations between 0 and 100,000, and then another 3 cities between 100,000 and 200,000, but then just one between 400,000 and 500,000, one between 1.3 million and 1.4 million, one between 2.2 million and 2.3 million, and another one, oh sorry, I missed, there's an even bigger one there. Another one between 4.4 and 4.5 million. So the range is still so great that in order to actually draw this histogram and fit it on the page, we've put a little concertina of the x-axis in between there, so we're not even really getting the sense of quite how far away that one is compared to the rest of the data. So it's sort of not, it tells us something, but it's quite difficult to draw initially. It's also a little bit meaningless. Even if we were to increase the width of the class intervals to try and avoid having to do this, the problem we would have there is that, these all get lumped together now into the one group. And so then, it becomes, you're not getting that distinction between, okay, we've got quite a lot of small cities, but some are quite small and some are a bit less small. If we were to go to 500,000, that one would get grouped in with those as well, and then you'd have just one big lump here and then just one and one somewhere else, and that's really pretty useless. So the problem is around this large data range. So what we actually need here is a non-linear scale. So that means a scale that doesn't just count up by adding. Okay, so in this first histogram here, this counts up now because these are by 100,000. We're adding on 100,000 every time. Okay, so that's 10,000, 100,000 every time, plus 100,000, plus 100,000, plus 100,000. In this one, we're adding on 200,000 every time. So that's plus 200,000, plus 200,000, plus 200,000, plus 200,000. Okay, so what we actually need is, rather than the scale counting up, plus 1, plus 1, plus 1, plus 1, plus 1, we need it to increase more rapidly than that. So it would be useful if it were to multiply, and obviously scale factors of 10 are sort of, they work quite nicely with our decimal number system. So if we could draw a scale that counted up in this kind of way, so instead of adding on 1 every time, we multiplied by, say, 10 every time. So 1, 10, 100. And what you would then be getting a sense of is not so much the value of each of the numbers, but the scale of each of the numbers. Okay, so if you had a histogram here with a few things there and a few things there and a few things there, okay, there's a lot of cities between 100 and 1,000 people. There's another couple of cities between 10,000 and 100,000, and another couple of cities between 100,000 and 1 million. It gives you a sense of, okay, you can basically say, tiny cities, medium cities, big cities, sort of thing, whatever it might be. So it's giving you more a sense of the magnitude or scale or size of the numbers, which is important when you've got data over a large range. So if we used this multiplying scale for our histogram about population, it would look like this. And again, in terms of sort of shape, and it's quite flat and it maybe doesn't say much, but it certainly gives us a sense of the scale of the cities we're dealing with in the list. We know that we have 4 cities with populations between 10,000 and 100,000, another 4 cities with populations between 100,000 and 1 million, and another 3 cities with populations over 1 million, or between 1 million and 10 million. So, as I said, we get a sense of the magnitude or the scale of the numbers rather than of their specific values. You know, we could probably say, you know, small cities or towns, medium cities and big cities. Do you know what I mean? Okay, so a multiplying scale such as this is called a logarithmic scale. And we don't usually label the scale with these values. We often use log in the scale. We'll talk about that. Or we scale the... Yes, we write it differently. We'll talk about that. Before we move on to that, though, we've actually seen 2020 and all the events that have happened have actually revealed to us quite a lot of graphs with logarithmic scales, whether or not you've noticed it. I'm just going to pause the video and flip over to a website for a minute just to show you. Okay, so here I am at abc.net.au. It's part of their coronavirus numbers charts and data section. And here we've got this first graph I'm going to show you is the number of confirmed cases by country on a linear scale. Okay, so that's the scale we're familiar with. So what I mean by that is if we look, I can't draw on this screen, but if we look here on the vertical axis, the scale goes up in a linear fashion in that each unit is, we're adding on. So plus 5 million, plus 5 million, plus 5 million, plus 5 million, plus 5 million. Okay. Now, the problem we have with this kind of scale when we're dealing with the coronavirus data, particularly when you're looking at trying to compare countries, is that the difference in case numbers between different countries is significant. Okay, so, you know, some countries like us have only had, you know, 1,000 or so cases. Some countries like the US have had millions and millions of cases, and trying to represent those numbers all on the same axes is challenging. And as you see here, when you use a linear scale, essentially what happens is all that we can really see is that the US has got heaps of cases, Brazil has also got a lot of cases, UK, Russia, Spain and Italy aren't doing too badly, and everyone else is lumped together down below, and it's all so close together that we can't even see them. So the solution here is rather than use a linear scale on the vertical axis, and most of the graphs along this line that you see, if you look closely at them, they are actually using a log scale. So I'm going to scroll down, it'll show the same data in a log scale. And so here what you see, now you can see how we can see the difference between the different countries. Obviously we're not getting that sense unless we understand the log scale of quite how many more cases the US and Brazil and interestingly India didn't appear on that other scale. Perhaps the data's updated slightly differently on each graph. So you're not getting the sense of quite how much more they are without properly understanding the maths behind the log scale. But we are able to see more countries and a bit more nuance in the data here. So you see on this vertical axis we're now using a log scale whereby it's not adding on a number each time, it's being multiplied by 10 each time. So we've got, you know, 100 cases is essentially the x-axis, 1,000 cases, so times by 10 is the next unit, 10,000 cases, so times by 10 is the next unit, 100,000 cases, 1,000,000 cases, sorry I said we've had 1,000 cases, that's a lie, but anyway, 1,000,000 cases and 10 million cases. So it allows you to, it gives you more space in which to show the differences between countries. So just out of interest, it's, you know, this is not an arbitrary out of nowhere thing that you'll never see anywhere. This is actually used quite widely in statistics because it's a really useful scale by which we can display data over a significant range. We'll talk about another example a bit later on, the Richter Scale, when we talk about earthquakes. That's actually a log scale as well. Alright, I'm just going to pause and jump back over to the notes. Okay, so I guess the question before we think about creating a logarithmic scale or a log scale is, what is a logarithm? Now really in further maths you don't need to have an understanding of what a logarithm is in order to be able to execute a log scale, but it actually makes it easier to answer some of the questions around log scales if you have a bit of a sense of what's going on. Bearing in mind, obviously you've always got a CAS, we'll talk about that in a minute, but as I said, a sense of understanding will help you. So logarithms are related to exponentials. So they're essentially opposite functions. So in the same way that addition and subtraction are opposites, logs and exponents, so by exponents I mean powers, are opposites. Any fact that you can write using exponents can be rewritten using logarithms. So we all know that 3 squared is equal to 9, and the equivalent logarithm statement with that information is log base 3 of 9 is equal to 2. So that's the same as me saying anything that I can write with addition, so we all know that 2 plus 3 equals 5, I can rewrite that in a different order with a subtraction. So that's the same as saying that 2 equals 5 minus 3. So that's essentially what I'm doing from here to here. It's the same information, just written in a different way using a different operation. You know, if I can say that 2 times 5 equals 10, then I can rewrite that using division as well and say that 2 equals 10 divided by 5. Okay, so it's essentially just a reshuffling of the same information. If 2 to the power of 3 equals 8, which it does, that means that log base 2 of 8 is equal to 3. If 3 to the power of 4 is equal to 81, that means that log base 3 of 81 is equal to 4. Essentially, this is saying, what power do I have to raise 3 to get to 9? 3 to the power of what gives me 9, and that's 2. 2 to the power of what gives me 8, that's 3. 3 to the power of what gives me 81, that's 4. Okay. In statistics, we tend to stick to using logs with a base of 10. It's an easy base to work with because of our decimal number system. And so let's just think about what we know about powers of 10. Okay, so we know that 10 to the power of 7 is 10 million. So the equivalent log statement is that log base 10 of 10 million is 7. So if you wanted to represent 10 million on a log scale, you would use 7. Okay, we'll talk about that. 10 to the power of 6 is a million, which is equivalent to saying that log base 10 of a million, 1, 2, 3, 4, 5, 6, is 6. 10 to the power of 5 is 100,000. That's equivalent to saying log base 10 of 100,000 is 5. 10 to the power of 4 is 10,000. That's equivalent to saying that log base 10 of 10,000 equals 4. 10 to the power of 3 is 1,000. That's equivalent to saying log base 10 of 1,000, 1,000 equals 3. 10 squared is 100, so log base 10 of 100 is 2. 10 to the power of 1 is 10, so log base 10 of 10 is 1. 10 to the power of 0 is 1, and so log base 10 of 1 is equal to 0. Then we get into the negative powers. 10 to the power of negative 1 is 1/10, 1 divided by 10, or 0.1. So log base 10 of 0.1 is negative 1. Log base 10 of 1/100th, which is 0.01, is negative 2, etc., etc., etc. So when we're working with the log scale, these are the numbers that we're going to see on the scale, and they correspond in terms of real numbers to these. Okay, so let's have a look here. So let's go back to our information about the population of the list of cities. If we calculate log base 10 of that population, and you won't need to do this because we'll talk about, it's really just about understanding, does that data value lie between 1,000 and 10,000, or is it between 10,000 and 100,000? Which powers of 10 is it between? So for example, this first one here we've already calculated for you, log base 10, let me just type it in my calculator, so the logs are over on the left hand side, it's above the 10 to the power of x because it's the inverse of that. So log base 10 of, if I typed in that 49079 and press Control Enter to get it as a decimal, to one decimal place it is, and that specifies that here, it is 4.7. So that makes sense because we know that log base 10 of 10,000, 10,000 is 10 to the power of 4, so that's 4. And we know that log base 10 of 100,000, sorry, I don't have zeros there, yeah, is 5. And this number is somewhere between 10,000 and 100,000. Okay, so that's why it is somewhere between 4 and 5. Okay, so we can calculate the log base 10s for each of the values. So log base 10 of the next number is 55,364, Control Enter, also 4.7. We could have predicted that. Let me just jump ahead and pick a different one, and then I'll pause the video and fill them all in and come back to you. Okay, so let's say jump ahead to, this Cairns one. So log base 10 of 146,778. Now I know that 146,778 is between 100,000 and a million. So that's between 10 to the power of 5 and 10 to the power of 6, which means that it is going to be, the log value should be somewhere between 5 and 6, which it is, 5.1. Makes sense that it's a low decimal. It's much closer to 100,000 than it is to a million. We would expect this number here, it is between 1 million and 10 million, so it's going to be somewhere between, which is 10 to the power of 6 and 10 to the power of 7, so the log value should be somewhere between 6 and 7. 4,440,328. Oh, sorry. Log base 10 of that. Log 10 of that. Control Enter. Yep. 6.6. Okay, let me just pause the video and I'll fill them all in and then we'll come back. Okay, so I filled in all the data. You'll notice here I just made a little note here because when you calculate log base 10 of 98,543, it's 4.994. Now this question specified that we should round everything to one decimal place. So to one decimal place that rounds to 5, but I just wanted to note that to be a bit careful about that because 10 to the power of 5 is 100,000 and this value is actually less than 100,000. So I'm actually going to be a bit careful here because, and you'll see this when I've grouped the data in the frequency table, I actually need to group this, and it's purely just because of the rounding, and I should have been a bit more careful about that, maybe asked for it to 2 decimal places instead, because actually that data value won't go into the between 5 and 6 bar of the histogram. It should stay in the between 4 and 5 bar of the histogram, so just to be a little bit careful about that. So as I said, then we can group the data and create a histogram. So we can group the log data where we look at between 4, from 4 up to but not including 5, from 5 up to but not including 6, from 6 up to but not including 7. And we see obviously the first group, as I said, we're going to count that in the 4 to not quite 5. These will all go in the 5 to not quite 6, and these in the 6 to not quite 7. As I said though, you really should be able to, you shouldn't actually need to calculate all these values if you have some understanding of what the logs are. And that's the point I was trying to make earlier. We know that 10 to the 5 is 100,000, and that's the barrier for 100,000 there. Okay, we know that these are all bigger than 10,000, which is 10 to the power of 4. 10,000. And these are, here's the barrier where we get hit a million, which is 10 to the 6. Okay, so on the log scale, it's going to be 4, 5, 6, and obviously 7 down here would be 10 million. So you shouldn't actually need, it's quite time consuming to bother typing all those numbers into the calculator. What you should be able to work out is this number is between which 2 powers of 10 to work out which group it goes into. So here we get our histogram. Now again, it's not showing us lots and lots of things. We already looked at this histogram before, but it does, we looked at it before where we had these labelled as 10,000 and 100,000, but generally speaking, we label them as 1, 2, 3, 4, 5, 6, 7, 8, etc. And the scale becomes log base 10 of the population. Okay, so remember log base 10 of 4 is 10,000, so that's representing 10,000. Log base 10 of 5 is 100,000, so that's representing 100,000. Log base 10 of 6 is a million. Log base 10 of 7 is 10 million. Okay, as I mentioned earlier, a common example, another example of the log scale is the Richter scale. The Richter scale is used for measuring the strength of earthquakes, but for every 1 point increase in the Richter scale, the magnitude of the earthquake increases by a factor of 10. So if you've got an earthquake with a Richter scale measurement of 3, and then another earthquake with a Richter scale measurement of 4, that's not just a little bit more of an earthquake, it's 10 times as big an earthquake. Okay, so the scale goes up in factors of 10, multiples of 10. An earthquake with a vibration amplitude that's, 2 million times greater than the normal vibration amplitude would be classified as 6.3. So it's you take, so if the Earth is vibrating all the time, but an earthquake is obviously when it's vibrating more than usual. So if it's 2 million times more than usual, that would be log base 10 of 2 million, 6.3 on the Richter scale. Okay, so that's what that number actually means. So if we know that an earthquake is 3 on the Richter scale, that means the actual vibrations are what's going on in there, that number in there. So if we got our CAS to solve that, solve log base 10 of an unknown value equal to 3 for x, that means that the vibrations are 1,000 times more than normal in that earthquake, than the Earth's normal vibrations. But then if you went to a Richter scale of 4, you would find that it's not just a little bit more, it's 10 times more, 10,000 times more vibrations. Okay. Alright, let's work our way through some examples to finish off. The average weights of 10 different species of mammal are shown in the histogram opposite. Due to the significant variation in weight between the species, a logarithmic scale has been used. So the scale is log of the weight, which means this in kilograms, which means this 2 here doesn't represent 2 kilograms, it represents 10 to the power of 2 kilograms. So that's 100 kilograms. This is 10 to the power of 3 kilograms. I should also say, so I've been writing log base 10, when we omit the base, when we don't write a base on a log, the assumed base is 10. So we can just write, in further maths we're only going to use base 10, we can just write log weight, meaning log base 10. Okay. But that means, 10 to the power of 2, 10 to the power of 3, 10 to the power of 4, 10 to the power of 5, 10 to the power of 6, 10 to the power of 1, 10 to the power of 0. That's essentially how we can read the scale, if we just want to know what the actual weights are. Okay, of these 10 species, how many different species have an average weight between 100 kilograms and 1,000 kilograms? Okay, so 100 is 10 to the power of 2, and 1,000 is 10 to the power of 3. Okay, 10 times 10 times 10 for 1,000, 10 times 10 for 100, which means that we're looking between 2 and 3 on the log scale. Okay, so 2 and 3, so that means there are 3 species, so this bar here, 3 species with average weights between 100 and 1,000 kilograms. The heaviest species included in the data is the blue whale. What can you say about the weight of an average blue whale? Okay, so we can see that there's one species up here, and that's the heaviest one, so that must be the blue whale. And so the blue whale weighs between, so it's between 5 and 6, which means its actual weight is between 10 to the power of 5, which is 100,000 kilograms, and 10 to the power of 6, which is 1 million kilograms. Okay, so we have the interval between within which we know the blue whale sits. Okay, C. The average kangaroo typically weighs around 70 kilograms. Calculate, correct to 1 decimal place, the logarithm, base 10, of the kangaroo weight, and hence determine the interval in which it would be included on the histogram. Okay, so this question actually asks us to calculate the specific value, but we could answer the second part. If it just asked for the second part, determine the interval within which the weight would be included on the histogram, we wouldn't actually need to calculate log base 10 of 70 kilograms. Because I know that 70, in terms of what powers of 10 to 70 lie between, 70 lies between 10 and 100, okay? And 10 is 10 to the power of 1, and 100 is 10 to the power of 2. So that would mean it would be between 1 and 2 on the log scale. Okay, but it does ask us to calculate, correct 1 decimal place, the log of the kangaroo weight. So we can confirm that, log base 10 of 70, we'll type that into our calculator, log base 10 of 70, control enter for a decimal value, and we want the answer to 1 decimal place, so that is 1.8. It's not kilograms, that's the kilograms in there. This is just a measure for the axis. There's nothing, the kangaroo doesn't weigh 1.8 kilograms, it weighs 70 kilograms, which on our log scale is equivalent to a value of 1.8. And so that marries with what we considered just by thinking about the size of the number we were dealing with. Okay, question 2. The Richter scale measures the magnitude of earthquakes using a log base 10 scale. How many times stronger is an earthquake of magnitude 8.1 when compared with an earthquake of magnitude 6.9? Give your answer to the nearest whole number. Okay, so we know that an earthquake of magnitude 8.1, let's work out what that actually means. So log of an unknown value is 8.1. So that means that that unknown value is, let's do a quick solve. If you know how logs work, you can just work, the answer to this will be the same as 10 to the power of 8.1. Okay, so let's see, 1, 2, 5, 8, 9, 2, 5, 4, 1. Just going to round that to the nearest whole number there, but I'm going to use the exact numbers in my CAS if I can. So it's about 125 million times the usual vibrations. As I said, if you know how your logs work, you don't need to get your CAS to solve that. To solve that, you're doing 10 to the power of 8.1. You can just straight away type that in. Okay. We also have another one, log of another unknown value. I'm going to use a different letter because it's not going to be the same value, is 6.9. So that means that that value, the size of that earthquake, I can just still use x in my CAS just to make it easy so I don't have to edit the equation. Let's get it equal 6.9. Alright, so that is 7,943,282. This was 0.2, this was 0.3. As I said, again, you could calculate that just by doing 10 to the power of 6.9 if you know how the logs work. And we want to know how much bigger is this times how much to get from that to that. Okay. So to work out what do I have to multiply the smaller number by to get to the bigger number, we're just going to divide them. So we're going to do 125,892,541.2 divided by 7,943,282.3. I've got those numbers sitting in my CAS, so I can just do that divided by that. And therefore it's approximately, now we want to answer the nearest whole number, it's approximately 16 times stronger. Okay, so 8.1 and 6.9, it's, you know, you're adding on 1.2, but that doesn't mean that it's just 1.2 times, sorry, that doesn't mean that, it doesn't mean that it's just 1.2 times as big, it's 16 times as strong. Another common log scale is pH scale. The pH scale measures acidity using a log with a base of 10 scale. So for each unit of decrease in pH, the acidity of a substance increases by a factor of 10. So if you've got a pH of 3 and it goes to a pH of 4, sorry, I've gone the wrong way, pH of 4 and it goes to a pH of 3, so it's going down, it's getting more acidic, so 10 times more acidic. Right, if a liquid's pH value changes from 4 to 3.3, by what factor has the acidity increased? Okay, so again, it's a log thing. So log of the actual value is 4, which means that the actual acidity value is, I'm not sure how acidity is actually measured, like what the actual units are. Obviously we record it in pH, but I don't know what the actual amount means. I have to ask a chemist. So if I solve this, if we know how the logs work, that's just going to be 10 to the power of 4, which would be 10,000. But we should be able to confirm that. So if I do, I'm just going to take this equation up here and edit it. Log base 10 of an unknown value equals 4. That means that unknown value is 10,000. Log base 10 of a different unknown value is 3.3, which means that that unknown value has to be 1,995.3-ish. Okay. And we want to know by what factor has the acidity increased. Okay, so we essentially want to know what's the scale factor here. What are we multiplying by? Okay, so 10,000 divided by 1995.3. I might just type a few more decimal places than that just to be sure. I'm just copying it from the line above, 2623. And so that's about 5 times more acidic. As we drop from a pH of 4 to 3.3. The acidity is increasing not by 0.7 but by, it's 5 times more acidic. Okay, last question. The table opposite shows the average weights of 10 different animal species. Display the data in a histogram using a logarithmic scale with a base of 10, with class intervals of width 1 unit. Okay, so let's get a sense about our smallest number here is 0.4, so that's going to be somewhere between 0 and 1. Okay, so yeah, we need, so powers of 10 are a bit tricky around 0, so obviously we know that 10 to the power of 0 is 1, and 10 to the power of negative 1 is 0.1, so it's going to be somewhere between those two values. Okay. Then we're going to need to go, what's our biggest value? 70,000. So that's somewhere between 10,000, which is 10 to the power of 4, and 10 to the power of 5, which is 100,000. So in terms of our class intervals, I haven't left us a lot of room here. Let's just be careful. Let's draw our table down here. So I'm going to do the log weight and the frequency. And we're going to need to go from -1 up to almost 0, 0 up to 1, 1 up to, sorry, not 0, my apologies. So it goes from, sorry, I'm confusing myself. So the powers are what we're recording. So -1 to 0 is the smallest grouping I need. And it won't actually be up to 0. The 0 will be in the next category. So 0 is 10 to the power of, so then we're going from 0 to 1, and then from 1 to 2, and we need to go up to the biggest grouping we need is from 4 to 5. 2 to 3, 3 to 4, just move that table up a little bit, and 4 to 5. Okay, so -1 to 0 is somewhere between 0.1 and 1, and there's just the 1 value that's in that category. 0 to 1 means we're between 10 to the 0 and 10 to the 1, so that's 1 up to 10. So any weights that are between 1 and 10. Okay, so we've counted that one. There are 2 weights between 1 and 10. Okay. This next one, from 1 to 2, log 10 to the 1 and 10 to the 2, so that's between 10 and 100. Any weights that are between 10 and 100, so we've got 1, 2, 3 of those. 2 to 3 is 10 to the power of 2, which is 100, to 10 to the power of 3, which is 1,000. So any weights between 100 and 1,000, we've got 1, 2, 3 of those. Then 10 to the 3 to 10 to the 4 is between 1,000 and 10,000. We don't have any of those, but we do have the one, the fin whale, between 10,000 and 100,000. And then we can create our histogram. Okay, so obviously our horizontal scale needs to go to -1. Now you can, some people will still put this here and label -1 here. As I've said before, I think the origin should always be 0. So I would put the frequency scale here and mark -1, 1, 2, 3, 4, 5. Okay. Frequencies only need to go up to 3, so let's have 1, 2, 3. So this is frequency, this is log of the weight in kilograms. Between -1 and 0 there is 1. It's 2 between 0 and 1. 3 between 1 and 2, also 3 between 2 and 3, 0 between 3 and 4, and then 1 between 4 and 5. Okay, you might choose to shade or colour your histogram. Right, and there we've created a histogram with a log scale. There's some instructions here about how you can use your CAS to create the histogram with a log scale. I'm going to talk a bit more about this and how to transform the data later on. I think for now you won't have to create, I think you should be doing these by hand for now. It's just as efficient really. As I said, I'll talk more about this down the track when we look at data transformation. So the work today is from exercise 1D.